saints in lockstep.
This is the concept video for the trace determinant plane. So this is again for 2x2 systems. And this is the equation y prime equals a y, where A is a 2x2 matrix, A11, A12, A21, and A22. And this has a characteristic polynomial, lambda squared minus the trace times lambda plus the determinant of A. And this, if we set it equal to 0, gives us two eigenvalues, lambda 1 and lambda 2, which equals t plus or minus the square root of t squared minus 4d over 2. And the nature of the solutions, they depend entirely on t and d. As we saw in the last video, the phase plane portraits, the solutions had different behaviors depending on the eigenvalues, and the eigenvalues are determined by the trace and the determinant. So we can show this graphically. We have a plane where the x-axis is the trace and the y-axis is the determinant. We have the line or the parabola defined by t squared minus 4d equals 0. So that's where we get this equal to 0, and we have one eigenvalue t over 2. So putting that in terms of d, that's d equals t squared over 4. So that's what defines this parabola. And anything above this parabola is where t squared minus 4d is greater than 0, or in other words, d is greater than t squared over 4. And anywhere under this parabola is where t squared minus 4d is greater than 0, or in other words, d is less than t squared over 4. So these regions on this graph actually correspond to the different types of solutions we got in the phase plane portraits video. So t squared minus 4d equals 0. So if t squared minus 4d is less than 0, so it's less than 0, that means this is imaginary, and we get a complex solution. So then with our complex solution, we had three different cases. If this was 0, so if the trace is 0, that's along the y-axis, we got a center. If the trace was positive, we had a positive real part, and our solution spiraled out from the center, so we got a spiral source. If our trace was negative, we got a solution that spiraled into the center, so a spiral sink. If we had t squared minus 4d less than 0, or sorry, greater than 0, then this was also real. And then if our determinant was negative, so that means this part was very large, or this part dominated, that means that we got a saddle. the reason we have a saddle is because if D is negative, then this is positive. That would mean this whole thing would be a large quantity, and this plus or minus would ensure that we got a positive or negative eigenvalue regardless of what the trace was. If D was positive, then this quantity would go down, would decrease the whole value of this, meaning that the eigenvalues would either be both positive if the trace were positive, and two positive eigenvalues led to a nodal source, and if the trace were negative, then we would get a nodal sink. So this trace determinant plane just shows all of these different types of solutions graphically and make sure that we have covered them all. So each of these regions corresponds to a generic solution of the 2x2 system. And these generic solutions are saddles, nodal sinks, nodal sources, spiral sinks, and spiral sources. And everything that lie along boundaries, for example, along this parabola or along these axes that border each region, these are called these the borders. The borders correspond to what they call non-generic solutions. And that's just some terminology. That's pretty much all you need to know for the trace determinant plane.